So the second talk of this today's afternoon's seminars will be given by Professor Francois Leblanc, and I mean, you're teaching your professor at the Sorbonne, right? Is that right?
I'm a seniorist researcher, so I'm not a professor in that sense.
Yeah. But what I want to say is that the Professor Leblanc, he's an expert, very experienced scientist on the question, I would say, of the atmospheric, in particular, exospheric systems of all planets and satellites. And then I think he must have written papers on every single satellite on the exoplanets, exosphere. But then he did something very interesting earlier about comparing. I remember it's comparing the exosphere of the Moon and Mercury, which are somewhat different but the same. You could derive the same, same physics from them. But today I think he will tell us more about the lunar exosphere. So what can we learn from the lunar exosphere? Yeah, Francois, please.
Yes, thank you so much. So thank you, Professor Wing, to invite me. To invite me for this talk. So I will give you some flavor about the exosphere of the Moon. I mean, usually when we think about the Moon, we are thinking of rocky planets without anything else around. But I will show you, hopefully, that in particular, thanks to the two last decades, there has been a lot of new discoveries around the Moon, showing that this is the atmosphere, what we could call an atmosphere around the Moon, is not that so empty. And there is a lot of very interesting observables around the Moon, and that can be used to say a lot of things regarding this subject. So that's the title of my the goal of my talk today. And but briefly to start my presentation, I like to summarize, to give you an idea, a very quick idea regarding what is the environment of the Moon. I mean, from a purely exospheric point of view. So first, I mean, very simple things, the Moon orbit. So the Moon orbit is very interesting for when you look to the exosphere, because what you can see on this very simple picture, the Moon is going to go through different environments. Most of the time, it will be in the solar wind. So you will see what the solar wind is doing on the Moon in terms of exosphere. And beside that, there is a big part of the orbit of the Moon, which is also going through the Earth's magnetosphere. And there is something else which happens. And there's been observations showing that things are different during these two big portion of the orbit of the Moon. So I will go through some of this, some illustration of this, of the importance of the Moon orbits for that point of view. And then just to let's say, to start with a global subject of my talk today, I took this picture from a book which is probably in press or now, which is a book which is written by many authors, but one of the chapters is specifically dealing with the Moon exosphere, and what the title they used was the dust, atmosphere, and plasma at the Moon, to let you know that basically we are not anymore speaking of only an exosphere, so purely neutral atmosphere, but now we are speaking of an ion-exosphere, but also more interestingly, and thanks to the very last missions around the Moon, to a dust atmosphere. So there is many things around the Moons, and each of these things are telling us something about the way the Moon is interacting with the environment. So the environment of the Moon is obviously first the Sun. So the Sun is in terms of solar wind particles, so a permanent bombardment of the surface by cave protons and helium particles. There is storms acting on the Moon, and there is sometimes some signature of these storms in the exosphere, in the dust, in the ion environment of the Moon. And obviously, the third ingredient is the solar solar light. So in particular, the UV and X-rays have some clear impact on the moon surface as well on its exosphere. Beside that, you have a relatively complex environment in terms of electromagnetic environments. As I will show, there has been the discovery of some magnetic anomalies. So some past signature of maybe a dynamo at the moon, or some remnant signature of a trapped magnetic field in the crust of the moon. But this signature, let's say this structures, magnetic structure at the moon surface have an impact on its interaction with the solar wind. So entering in my subject, so my talk is really focused on the exosphere, and I like first to maybe for the people who are not very familiar with this object, what are we calling an exosphere? Basically, we are calling an exosphere the atmosphere of the moon because it is so thin, so the density is so low that particles are behaving in a very different way than particles in a classical atmosphere than the one of the Earth. And they are basically not colliding between each other, so they do not exchange any information on their energy, trajectories, compositions. So they are moving freely one from each other around the moon. So it makes the observation of the exosphere particularly interesting because their main, let's say, characteristic, what characterized them in terms of energy, spatial distribution, temporal variability, is directly related to what happens in the surface of the moon. So this picture in the bottom part of the slide here is showing you what's basically we believe is happening to particles which is being ejected from the surface. So you start from this point. You have, as an example, nitrogen particles which can be ejected from the surface. It can be ejected either on an escape trajectory, so having enough energy to escape the moon's gravity. But some of these particles, the heavier ones, are going to be still trapped gravitationally in the gravity field of the moon, and we'll go back to the surface and we'll do this kind of trajectory, which is a sum of hops moving around the planets up to the moment they can be either absorbed by the surface again up to a new ejections, or be ejected again on an escape trajectory. They can also be photoionized. They can charge exchange with particles, ions, or electrons around the moon. And a lot of things can happen to them. But basically, one more time, what we see in the exosphere is first an indication of some processes acting on the surface of the moon. So that's the way a lot of the observation has been interpreted so far. And that's one of the interests to observe the moon, the moon exosphere. So as I said, you have each particles is going to move in the exosphere, in the environment of the moon, freely from each other. So usually we are speaking of one exosphere as we are speaking of one atmosphere around the planet. But in the case of this particular object, an exosphere, what we can say usually is that in all spaces, I mean, because they are ejected differently from the moon surface, will form a different exosphere. So what we see, and I will illustrate that in the following slide, is that we have as many exospheres as spaces in the environment of the moon. So the first example is coming from some observations done by LADEE, in particular by the mass spectrometer, which was on board this NASA mission. The originality of this mission is that this instrument was very sensitive and has been able to measure very, very low density, as it is the case in the environment of the moon, and has been able to provide us some very long-term observation of the moon on which are illustrated on this slide. What you see here is two species, which are the helium and the neon, which has been observed by this instrument, on which are showing this variation of their density with respect to the longitude, so somehow with respect to the local time. So what I put in gray on these figures is the part which is corresponding to the night side of the planet, of the satellites. And what you can see from this figure, that the densest place for these two species is in the night side. And actually, this has been very well explained 40 years ago by the first missions which land on the surface, the Apollo missions, which were also carrying some mass spectrometer, on which I've measured some of these species on their cycle, their diurnal cycle in the exosphere. And they show also that these species were the densest, in the night side. And there has been a very simple model, or relatively simple model, to explain this diurnal cycle of the density, which has been developed by Hodges and Johnson in the 70s, which explain that basically the density is following such a type of relations, which is essentially proportional to a power to the inverse of the power of the surface temperature. In other way, the colder the surface is, the denser you have the exosphere. In other way, if you go back to this image of hops around the planets, around the satellites, sorry, the place where the surface is colder will correspond to the place where these particles will get colder and colder because they will exchange energy with the surface, and they will simply accumulate in the colder place of the planet. So, in other way, on the night side of the moon. So this is also very well explained by these bottom panels here, showing the relations between the temperature of the surface, which is a black line here, and the temperature of the exosphere as derived from the scale height of the density measured by NMS on LADEE. So there is a very nice explanation and very good understanding of the way these two species are let's say, organized spatially around the moon based on this simple law derived 40 years ago from the first Apollo missions. The pictures get a little bit more complex, and thanks also to the LADEE, because still in this, thanks to these instruments, and also to the existence at the same time of some missions, Artemis in that case, which were equipped with instruments able to measure the solar wind density in the same time than NMS was operating. And they show this excellent, impressive correlation between the moon flux, so solar wind flux, sorry, and the helium density as measured by NMS. In other way, what these measurements are showing is that the helium is organized around the moon with a peak in the night side, but the main source for the helium exosphere is the solar wind implantation in the surface. So in other way, it's the day side. You bombard permanently with the solar wind particles, with the helium particles from the sun. You bombard the day side of the moon. You eject some new helium particles, which are going to move around the satellite and will get accumulated on the night side. What is also very interesting in this observation is that from this observation, from the flux which is being measured in the solar wind, we can derive that the main source of the helium which is observed in the exosphere is indeed the solar wind. So 80% of what is seen in the exospheres come from the sun, but there is still a few 10% which are coming probably from the interior of the moon. So there is a mixture of exogenic and endogenic source in this helium exosphere. So it's another way. In another way, helium can also be used as a probe of the internal parts of the moon. Actually, there is also moving to another species just to illustrate you how different can be the exospheres for all these species. Another species which has been observed by Apollo a long time ago was the argon. So the argon is as dense as the helium around the moon in the exosphere. There has been some observation a long time ago by Apollo, but one more time, the NMS instruments told us very new things and very interesting things. So this figures is illustrating here again the density variation with respect to the local time. To the selenographic longitude in that term, not the local time, but it's organized in terms of sunrise. When the longitude at the surface of the moon was at sunrise, in the early morning in the way, or at post sunrise, so just before the sunrise, or in the night side. So what is shown here is the same, in another way, it's illustrated in another way, but it's showing the same cycle as shown for the helium or for the neon. You have a significant increase of the argon density as soon as it's different, sorry. It's relatively different because what you see here is that as soon as the sun is rising on the moon surface, the argon is extracted from the surface, so contrary to the helium and the neon. Helium and neon are not trapped in the surface, but here the argon is clearly trapped in the surface and gets released as soon as the sun rises on the surface. So you see this difference between the sunrise and the post-sunrise density, showing that as soon as the sun is rising, argon is getting extracted from the surface by the sun and probably by the photons of the sun. What is also very interesting in this observation is this bulk, what they call the bulk of argon in the night side. So in the night side, the density is much smaller because, as I say, the argon is getting trapped in the surface, so in some way stick to the surface because the surface is so cold that the argon get trapped, absorbed in the surface. But there is still something happening in the surface, in the night side, as illustrated here. With this clear peak of the density of argon when the longitude at the surface in the night side, and this peak has been associated clearly with this particular region at the surface of the moon, which is a creep region, so which correspond to a lower altitude of the moon surface, but also to an enriched region in potassium, according to the lunar prospector observations. So in other way, what is shown here, what illustrates these figures, the fact that there is a clear association between the moon surface and what is inside the exosphere, what can be observed in the exosphere of the moon. Which means that the exosphere can also be used as a signature of the variation of the content of the moon surface in terms of in volatiles. So this is also a very interesting suggestion that we can use observation like this to probe somehow the surface of the moon. Last things is regarding the argon, but also regarding the helium, is a suggestion that we could also use the moon exosphere observations to probe the activity of the moon of the interior of the moon in terms of earthquake. In other way, there has been some suggestion some times ago during the Apollo era that some of the variability observed in the moon exosphere could be related to moonquakes. This is also suggested by long-term observation by LADEE on NMS regarding the argon, which is illustrated in these figures. You see the cycle of the moon density in an average as observed by this mission, by the LADEE mission. And if you extract this variability, you can extract a kind of relative variation of this density along this many months of observations, showing a long trend in the argon content in the exosphere, which is also an illustration that this global variation of the argon in the exosphere could be related to some internal variability, I mean, internal activity, which release some argons, which change the structure of the upper surface of the moon, allowing some argon trapped in the regoliths of the moon to be released in the exosphere, which is then illustrated again by this long-term variability. So there is this idea that also we could probe the internal deeper in the moons inside the moon, thanks to observation of the exosphere. Last illustration of the moon exosphere is one of the best observed and easiest to observe species in the exosphere of the moon is the sodium component, the sodium exosphere, which has been so far essentially observed actually from the Earth, thanks to ground-based observations. And here you have some of this very nice picture which has been obtained by observers from the Earth. This one, as an example, is a very nice observation that show that the contrary to the argon, contrary to the helium or the neon, the sodium exosphere is organized in local time and is also almost symmetric with respect to the solar direction. So it, in other way, it tells us that what's the mechanisms which leads to the formation of the sodium exosphere, contrary to the other species I described so far, is the bombardment of the surface by the photons. And people believe that the main mechanisms which leads to the ejection is the photo-desorptions of the moon by sodium, photo-desorption of the moon surface of sodium atoms into the exosphere. So there is some observation. There is also a very nice observation showing that the moon exosphere is not completely only concentrated around the surface, but can be very elongated. And this is one of the illustration is this picture here showing how extended can be the moon exosphere. So what you see here is the moon here, and the extension of the light coming from the sodium atoms coming from the moon surface. What you have here is shown here is the Earth, because what people have observed as well is the way the gravity of the Earth has an impact on the spatial distribution of this long tail of the exosphere, leading to some peaks in the anti-sunward directions behind the Earth. When you look to the sky, you will see peak in light coming from sodium atoms. And actually, this is a gravitational effect which concentrates the tails in the anti-sunward direction behind the Earth. So that has been observed by many observers, and this is also a way to follow the variability of the sodium exosphere with time by looking to this spot in the anti-sunward direction behind the Earth. So actually, last things regarding this sodium, and actually the potassium is behaving in the same way. So still on LADEE, there was also a UV spectrometer, which was so as I said, the sodium and potassium are relatively easily observed from ground-based observatory, but can be also relatively well observed by UV spectrometer. So that was the case on LADEE. On this UV spectrometer has also provided a very interesting observation showing that something I said at the beginning of my talk, the effect of the magnetosphere of the Earth on the exosphere. So what is illustrated here is the variations of the sodium light intensity as observed by these instruments with respect to the moon orbit. So what is shown here is the moon orbits around the Earth. This orange part here is a part of the moon orbits inside the Earth's magnetosphere. And what is you can see here the fact that there is a clear effect of the Earth's magnetosphere on the moon content in terms of sodium and potassium. The way this observation has been interpreted is based on the idea that one of the main driver of the moon of the sodium and potassium is not only the photons from the sun, but also the solar wind particles, which do not act in terms of ejection. They do not, by impacting the surface, they do not eject directly sodium and potassium from the moon surface, but they change the surface content, the structure, and they allow the sodium and potassium to migrate through the regoliths up to the moment when the photons, the solar wind, can get back and act on the surface of the moon and release this sodium and potassium. So it's also very nice. In other ways, this orbit of the moon is being used as a kind of laboratory experiment because you change the configuration, the external configuration of the moon, and you observe what is the consequence on the exosphere, on the ways the volatiles trapped in the surface of the moon are being ejected after passing through the Earth's magnetosphere. The last things, which has been also very, which is related actually to the previous talk, is the possibility that on the moon, some places contains more water than the rest of the surface, and that's being observed by the lunar prospector missions. They look to the neutrons emissions from the surface and derived from this observation that some parts, and in particular the high latitudes at the moon, the high latitude craters at the moon could contain more hydrogen type of species in the almost permanently shadowed region at the surface of the moon. So in other way, that was an interesting suggestion that there might be some water trapped permanently in some of the region, which accumulate with time in this particular region at the surface of the moon. There has been some modeling, in particular this modeling illustrated by this picture here by Crader and Von Drack, suggesting that the main origin of this water trapped, permanently trapped at the surface of the moon was probably from solar wind origin. So in other way, it was a complex mechanisms of protons impacting the surface, reacting with the oxygen of the trapped, which compose the surface, the regoliths of the moon, producing some OH or H2O molecules, which then migrates around the moon up to the moment they were impacting these very cold regions at high latitudes in the craters of the moon. So, in other way, some suggestion that behind the species I described before, there was also some water in the exosphere of the moon. So, actually, one of the very interesting suggestions that has been, let's say, brought by these recent missions around the moon were that probably one of the main drivers, which I did not speak about so far, is the fact that the moon, as well as all objects in the solar system, are permanently bombarded by some very small grains, meteoroid of micron or 10 micron size, which permanently are bombarding the surface, leading to some particular interaction between these very energetic objects, which bring a lot of energy to the surface of these objects. And one of the signatures of this interaction might be the formation of an exosphere, or let's say the existence of some species in the exosphere of the moon. So thanks to LADEE, on LADEE there was an instrument dedicated to the measurement of the dust. I mean, in terms of composition, in terms of grain size, they were able to provide a lot of original information regarding the dust environment, the dusty atmosphere of the moon, which are illustrated here. So first, they show there was a very clear and very strong asymmetry between the dawn and the dusk of the moon. I mean, with a clear peak of dust in the exosphere of the moon at the dawn, which is the apex of the planet. So the place where basically the meteorite will impact. I mean, the flux of meteorite will impact will be larger for this object. So it's relatively easy to understand why we have this this peak at the dawn in terms of dust formation. What is surprising, what was very surprising from this observation was how strong was the asymmetry between the dawn and the dusk. There has been also some observations of signatures due to to some streams of meteorite at the moon. I mean, as an example, during the Geminids shower, there has been some clear association with the increase of the dust in the exosphere of the moon. Also, some monthly variability of the moon dust, also due to the orbit of the moon, due to the effect of the of the Earth, as well as some annual variability, which are also related to these particular moments where there is some strong shower of meteorite at the moon. Actually, this is also illustrated here by this measurements of the average impact rates on the instruments, on the LADEE instruments during all this period, all these months, showing that there is clear period of peak of impacts in association with some well-known meteorite shower acting on the moon, at the moon during this period. One thing which is being interesting is that there is still some let's say, non-observed population of dust, in particular the very small size, the nanoscale size dust, has been suggested by some UVS observations, showing that there is around the moon a population of very small dust grains which scatter the light from the sun, which are observable with a UV spectrometer, but which were not seen by LADEE instruments simply because they were too small. I mean, the instrument was not fit to be able to measure really well these very small size particles. So in other words, there is a whole population which is not well constrained, on which is particularly interesting, because if you think of these very small size particles, this is probably particles which last a lot around the moon because they are very light. So probably they are not gravitationally escaping, but they are moving around the moon, forming a very large clouds everywhere around the moon. So actually, this is the suggestion was that it was during the Apollo missions. There has been some observation of what they call lunar horizon glow, and this lunar horizon glow, so as seen from astronomers, the people who were on the moon surface at that time, they saw some glow, horizon glow, and they at that time there was a suggestion that it was a dust light reflected on dust, and actually the idea is that it might be this 10 nanometer size grains which are at the origin of this glow. So this is something which is still to be confirmed by other instruments or other information, but this is a very important information regarding what is really around the moon, and which could impact a lot of future missions, landers, and orbiters around the moon. So coming back to the exosphere, so what is the signature of this dust around in the exosphere? So there has been many observations of these signatures. I will take two of them. One is related to the sodium and potassium. So I say that the sodium and potassium probably are following some cycle of absorption, desorptions related to the moon orbit. So this is illustrated here again by this figure here, which is similar than the one I showed you before, showing you that that the cycle of the sodium density in the exosphere of the moon is clearly following the orbit of the moon. So there is this signature of the Earth's mesosphere on the content in sodium in the exosphere of the moon. But also that there is some suggestion that the meteoroid streams have a signature on the intensity of the sodium contents. It's illustrated here by these blue lines here, which show the moments where some large streams occur at the moon, showing that at the same time you have some peaks in the sodium exosphere. What is somehow puzzling, because I would not expect such a difference, but when you look to the potassium, so the same instrument was looking for the sodium and to the potassium light coming from the exosphere, and for the potassium, the signature of these meteoroid streams were really much stronger, much obvious, as illustrated here during these particular events. One thing which is also shown in this picture, that with one of the difficulty, let's say, to extract signatures in the exosphere related to different elements, to the meteorites, to the surface contents, is the fact that obviously everything is mixed in the exosphere. But what is seen here is the fact that behind the signature of the streams, meteorite streams on the potassium exosphere, you have this cycle, which is essentially related to the fact that the creep terrain, so this region which is enriched in potassium at the surface, is as a clear signature in the exosphere of potassium when this region are facing the sun. They released a lot of potassium in the exosphere, and this is a very clear cycle as in association with this particular region at the surface of the moon. So, but I think that one of the most interesting observation related to this signature of the meteorite on the exosphere content is related to this observation of a very clear and obvious correlation between the water content in the exosphere. So still on NMS, there's been a very nice work done by Benna on this for using the data associated with these instruments. What has to be said that this instrument was not built to measure directly the water content of the exosphere, but by using the fact that the satellite orbiting around such an object will trap some water as soon as there is some water in the exosphere. And what is measured here is the signature of these mechanisms of trapping of the water in the exosphere by the satellite, later released by when the satellite is getting hotter due to the solar light. And in association with these mechanisms, there was some NMS measurements which show that clearly there is an association between this, the quantity of water around the satellite on the occurrence of some meteorite streams. So in other way, it did show that the meteorite have a clear effect on the water content in the exosphere of the moon. What was also very interesting from this observation that they deduced that this water was not coming essentially from the meteorite themselves, but was coming from the surface. More precisely, was coming from a layer of the surface which was slightly deep in the ground, few centimeters below the surface, because let's say the association between the flux, their composition in terms of dust grains, size, and so on, and the content of water as measured by NMS, they deduced that the surface was composed of a layer of desiccated surface, so almost dry of water. And below that first layer of few centimeters, there were some surface which were enriched in water. And what was doing this meteorite bombardment was simply to dig into the surface to extract the water and to release it in the exosphere. So, in other words, there was they brought a much clearer view about the cycle of the water in the exosphere of the moon, thanks to this type of observations. So the last part of my talk will be dedicated to one of the third aspect of what has been observed around the moon is the ion-exosphere. So in other words, so far I essentially spoke about neutral particles, so electrically neutral particles. And now I will tell you a few things about the ions, so particles which are charged. The difference between ions and neutral particles is that it's much easier to observe them with some mass spectrometers than for the neutral particles. So there has been a lot of observations around the moon of these populations on telling us something different regarding the way the solar wind, the sun, is interacting with the moon. And the very first observation is this observation of on the Chandrayaan mission. There was an instrument which was able to measure what we call the energetic neutral atoms, which are simply neutral atoms. So not ions, but you will see this is related to the ion environment of the moon. So neutral atoms with some energy. So the instrument is sensitive enough to measure these neutral atoms as soon as they have a few hundred eV energy on larger energy. So what has been surprisingly observed by this mission, this Chandrayaan mission, was the fact that from the surface of the moon, there is a very strong reflected flux of hydrogen atoms. And the interpretation of this observation is that these neutral atoms, are essentially protons from the solar wind. So protons of the solar wind have kilo-electron-volts energy. They impact the surface. And before, people were thinking that these protons were implanted in the surface and were not re-ejected. And what happens actually is the fact that this almost 20% of this incoming protons from the solar wind are simply re-ejected from the surface with a slightly lower energy and being neutralized when interacting with the surface. So this is illustrated by this drawing here, showing that the sun direction is here, when the yellow part is a brighter, whereas it is yellow. So in other way, the reflected flux at the surface of the moon is essentially proportional to the solar zenith angle at the surface, so to the flux, to the intensity of the flux, which impact the surface, the surface at the position at the moon surface. So what they observe is essentially hydrogen neutrals energetic atoms, but also with a much smaller proportion, some helium atoms also reflected at the surface of the moon. What is interesting in terms of physics of the interaction of the solar wind particle with the surface is the energy distribution of this particles which have a specific energy distribution. So I said, as illustrated in this on this picture on this figures here, you have the solar wind energy typically around 1 keV energy, and you have all this population which extend quite to high energy, almost to the solar wind energy, down to very low energy, and probably even lower energy. The instrument on Chandrayaan was not sensitive below this energy. So there is probably a missing, here again, missing population, which is not being observed so far, but is probably there around the moon. So one of the nicest illustration of this measurement of the reflected hydrogen population is the fact that, as I said earlier during my talk, there has been some observations of the existence of some crystal fields, some localized magnetic structure, which are at the surface of the moon, and which basically interact with the solar wind, with the incoming solar wind flux. And what has been observed by this through these reflected energetic neutral atoms is the way this localized magnetic fields will deflect the solar wind. So this is illustrated by this drawing here, showing that the solar wind protons are bombarding the surface, but they get deflected when they encounter this magnetic anomaly, which lead to some surface charging. So people are predicting some very strong difference in surface charging between these two regions. So also telling us that some regions will be electrically very different from other ones at the surface of the moon due to the presence of these magnetic fields. But also they give us some very interesting information on the way these protons, when they arrived at the moon, will impact the surface and will get reflected on. And in particular, you see clearly that this the internal part of these magnetic structures are getting protected somehow from this bombardment of the surface. But the last thing that I would like to say regarding this ion exosphere is the fact that, as I said when I introduced these ion exosphere observations, instruments which are dedicated to the measurement of the ion exosphere are usually much more sensitive than neutral instruments. So in other way, by probing the ion exosphere contents, you are also probing the neutral parents exosphere, and you can discover some species which were not observed as neutral particles into the exosphere. So that's the idea here. Is this observation that I'm showing here is one of these illustration that what is shown here is the different species which have been observed by an ion spectrometer by the NIMS, which was also able to measure ions on LADEE. So they observe essentially most of the species which has been also observed as neutrals, except this what they call carbon-bearing molecules. So most probably CO+, but could be other species, and showing that this species is one of the most abundant in the exosphere. In other way, what I show you so far was some observation of the neutral exosphere, but it seems, according to this ion exosphere, that we are still missing one of the most abundant components in the exosphere of the moon, which is probably carbon-bearing molecules, and which suggested by this ion exosphere. Some analysis of some measurements by LADEE, still by the NMS instruments, were that it could be CH4, the methane, but I don't think this is completely shared by everyone. And I think basically we can still say that this carbon-bearing molecules is still very poorly observed, is not known. And in particular, we don't know how this particle is being ejected in the exosphere. What we know is that this is probably one of the most abundant species. And to complete this picture of the ion exosphere, the last things which has been observed, that besides this ENA in particles which being reflected, coming from the solar wind reflected as neutrals, there are still a small percent of these solar wind particles which are also backscattered by the surface. So in other way, the picture we had, let's say 20 years ago, of a surface like the moon, which absorbs essentially the solar wind particles, is not true. Basically, what's happened is that a lot of particles are being rejected from the moon surface as soon as they impact it. So to conclude, here almost my last slide. The message I would like you to get from this talk is simply that what has been shown thanks to the, let's say, the last 20 years of observation of the moon of its environment, is that this environment is far from being empty, as we thought before, that there is some dust, a lot of dust actually, very complex organized dust with time variability, spatial variability. There is many species which are being observed. So I illustrated some of them. The way here, what you are seeing is some modeling of the neutral density in the equatorial plane. So showing the different ways these species can be organized around the moon, with helium peaking on the night side, as I said earlier, with the argon released in the early day side, with sodium peaking on, as well as the potassium peaking at noon. So all species being organized differently depending on the way they interact with the surface. And also a relatively complex, much more complex environment that was thought before in terms of ion-exosphere around the moon. So my last slide, my conclusions, basically complex on the rich environment is around the moon. I think that a lot of this observation can be related to some information regarding the surface compositions, the internal activity as well. This idea that some regions in the polar regions can be the place where some volatiles get accumulated. That the moon exosphere is also the best probably laboratory for the exploration of our solar system. I mean, in the sense that this is the best place where to observe how a solid surface interact with its environment. Obviously, all this observation will help us to understand better how the moon environment can be difficult to bear with. I mean, knowing all the many future ground missions which are planned in the futures. And the last thing, which is also that people suggest, is also maybe because of all these future ground missions, we will change for a long time this environment that we are observing now. In other ways, coming back to this idea that this, as an example, this very nano-sized dust can be released from the surface of the moon and might last around the moon for days or months. You can imagine that as soon as a spacecraft will land on the surface, it will release a lot of materials from the moon that can last for quite a long time, changing somehow for a long time what we know so far about the moon. So that was my last slide, and I thank you for your attention.
Yeah, thank you so much, Francois. I haven't seen the next speaker coming online yet, so we could have asked a few more questions here. Anyone have questions? Please unmute yourself and ask the questions. The one question I have is that even though you talk about different kinds of elements and ions, and the one thing missing is the calcium.
That you mean I mean, you mean that that's been observed around the
Mercury.
Mercury?
Yeah, but then the funny thing, of course, with Mercury, the calcium atom observed at Mercury is very hot.
Yeah, absolutely. And this is probably also a product of the meteoroid bombardment. You're perfectly right. There is beside that, there is also some at Mercury. If we make this parallel with Mercury, there is also the aluminium, which has been suggested from ground-based observations around Mercury. I mean. Magnesium has been observed. So there is still, you're right, besides this carbon-bearing particle, there is also other species which are still missing in, and probably there around the moon, but never observed so far. Absolutely.
Right. And then the Rosemary Killing has the theory that those are very hot calcium observed at Mercury came from this dissociation of some calcium oxide or some calcium, related molecules. So I'm always wondering if they were created by meteor impact. Similar stuff should be produced at the moon also. How come we don't see them?
Yes, absolutely. Actually, I show some NMS ion measurements, but there's been some wind measurements some times ago, suggesting that they suggest to have observed also silicate type of ions as well as aluminium, so coming from the moon. So clearly, there is a lot of things to observe still now. On species which have not been observed. And I think the interesting situation with the future, the forthcoming VIII Colombo mission around Mercury, with many instruments which should provide us a much clearer view about the Mercury environment, will help us also to predict something about the moon, the moon environment. Yeah.
In your conclusion slide, I mean the second from the last, we were comparing the argon, helium, and all that. I thought you would be talking about that part of the modeling also in your most recent paper.
I think that it was more. That's true. I could have dedicated how this we understand the details of the mechanisms leading to the formation of these exospheres. But I thought that I thought very interesting the fact that after 40 years after the Apollo missions, the moon environment has not been observed, and it is only during the last decade that many new observations has been performed around the moon, and honestly they changed quite a lot our view about this environment, and so I thought that it was very interesting also to illustrate that we have still a lot of things to learn about this particular object.
Yes, certainly. Thank you so much. I still have a couple of questions to ask you, but I could write to you. Yeah.